circuits. Part 5, the RLC circuit.
In the last video, the RL circuit was thoroughly examined.
Two fundamental types of relationships were shown to be at the core of all RL circuit analysis: phase relationships and Ohm's frequency relationships. You were shown formulas for calculating total voltage, current, and impedance. The effects of a variable frequency were demonstrated, forming either a low-pass or a high-pass filter.
By now, you're familiar with RC and RL AC circuits. In this video, all three devices will be connected into one circuit called an RLC circuit.
RLC circuits will be analyzed in both series and parallel configurations. Two primary types of relationships that will be useful guides for analyzing any type of RLC circuit will be presented. Impedance will be calculated. Finally, you'll see how varying frequencies affect voltage and current within RLC circuits.
Again, it's important to realize no matter what combination of resistors, inductors, and capacitors an RLC circuit may have, that each device will always respond as itself. All of the advanced AC circuit concepts that will be presented in this video are derived from fundamentals that you've already learned. Let's begin by taking a look at a series RLC circuit.
This circuit consists of a resistor, an inductor, and a capacitor connected in series with an AC voltage source. Whenever you examine a series circuit, you know that the current is the same throughout, according to Kirchhoff's current law. The source, resistive, inductive, and capacitive currents are all equal. They are identical in both magnitude and phase.
Next, the same two fundamental types of relationships which were presented in connection with RC and RL circuits will serve as useful guides with RLC circuits as well. They are phase relationships and Ohm's frequency relationships. This is because they will always hold true no matter what configuration of resistors, capacitors, and inductors you find. At this point, it's helpful to review each component's characteristics separately. Let's review the phase relationships on graph paper.
Recall that the voltage across a resistor is in phase with the current in the resistor. But remember that the inductive voltage leads the inductive current by 90 degrees, and the capacitive voltage lags the capacitive current by 90 degrees.
Let's look at all three graphs together to draw some conclusions about the voltage drops in an RLC circuit.
Since the inductive voltage leads the current by 90 degrees, and since the capacitive voltage lags the current by 90 degrees, this means that the inductive voltage and the capacitive voltage are exactly 180 degrees out of phase. The combined voltage across the capacitor and the inductor can be found by subtracting them. As an example, suppose you have a series RLC circuit where, at a given frequency, the inductive voltage is 12 volts and the capacitive voltage is 10 volts. To find the combined voltage across the inductor and capacitor, subtract V sub C from V sub L. 12 volts minus 10 volts equals 2 volts.
Let's consider an example where the capacitive voltage is greater than the inductive voltage.
In this example, the voltage across the inductor is 10 volts AC, while the voltage across the capacitor is 15 volts AC. The same formula is used because in a series RLC circuit, the capacitive voltage is always subtracted from the inductive voltage. 10 minus 15 yields minus 5 volts. The minus 5 indicates that the combined voltage across these two components is lagging the circuit current. If the result is positive, then the resulting voltage, which is primarily inductive, will lead the circuit current. If the result is negative, then the resulting voltage, which is primarily capacitive, will lag the circuit current.
Now let's determine the total voltage in a series RLC circuit when the AC voltage across each circuit component is known.
Since the resistive voltage is always in phase with the circuit current, And the resulting combined voltage across the inductor and capacitor will always be 90 degrees out of phase, either lagging or leading. Then phase relationships can be used to determine the total voltage in an RLC circuit. The total voltage in a series RLC circuit, V sub T, is equal to the square root of the resistive voltage, V sub R, squared, plus the resulting voltage across the inductor and capacitor, V sub L minus V sub C, quantity squared.
In an example series RLC circuit, the resistive voltage is 4 volts, the inductive voltage is 9 volts, and the capacitive voltage is 12 volts. Substitute these values into the formula to get V sub T equals the square root of 4 squared plus the square of the quantity 9 minus 12. This is the same as the square root of 4 squared plus minus 3 squared, or the square root of 16 plus 9. Note that squaring the negative voltage that represents the combined voltage across the capacitor and inductor yields a positive number. This is because a negative times a negative always produces a positive result. Complete the calculation to get the square root of 25, which means a total voltage of 5 volts AC for this circuit.
Stop the program and complete activity number 1. When finished, continue watching the program.